Log on, tune in, find out. Another good idea from Cambridge.
It's a pleasure for me to talk about, this is, by the way, joint work with Philip David and Luisa Bernardinelli of the Statistical Laboratory here in Cambridge. I will talk about methods of causal inference which are useful in the analysis of data from observational epidemiology, and more specifically data from genetic epidemiology, with particular attention to those investigations where the aim is to get a better understanding in molecular mechanisms of disease, something which is usually done in alliance with biologists. I will set the scene with a very simple example. Here we have this pi, which represents the unknown probability of a disease, and is modeled to depend on exposure variables A and B according to this logistic model, but the choice of the model is not essential to the discussion. And you see that this model contains an interaction parameter. When delta, the interaction parameter, departs from 0, which means that there is a departure from additivity on this particular scale, we say there is statistical interaction between the two exposures A and B. But we know that this interaction can come and go with a change of the scale of the model, and so we all know that it's very dangerous if we interpret this interaction between A and B, this statistical interaction, to indicate an interaction at a deeper level, biological or physical, in the sense that A and B participating in a common mechanism, for example. Yet, despite this caveat, it's very frequent, or it's not infrequent in, for example, in the epidemiologic literature, to find authors which hail a significant statistical interaction as a significance also at a deeper level of mechanism. And let me illustrate this with this example. The story here in this slide involves a gene called FTO, which is known to affect risk of infarction, essentially because it makes you hungry and possibly obese. And there is evidence that in those people who do a lot of physical activity, the effect of this gene on infarction is attenuated, which is an example of statistical interaction, basically. And for what we have seen earlier, it would be dangerous to interpret that in terms of mechanism. Yet, it has been claimed, this evidence has been used in support of these two hypotheses, which are examples of mechanistic interaction. In some individuals, the deleterious FTO variant will lead to infarction if they do not start doing physical activity. This is mechanistic interaction. And here, we even see the argument going to the level of molecular mechanism. Physical activity has the power of downregulating the expression of gene FTO. So there is this temptation to use a statistical interaction to support hypotheses which actually have to do with mechanistic interaction. So before proceeding, let's see, what does mechanistic interaction, how can we give it a mathematical formula? Well, for the simple case in which A and B, the two exposures, are binary, a possible definition is this one. A and B are said to interact mechanistically, not only statistically, if there is a joint setting for A and B that produces disease, but would produce no disease if either A or B were changed. This is not the most general definition, but it's a good one for my purposes. So let's go back to our logistic model. The question is, are there statistical tests for detecting mechanistic interaction in the sense I've just defined? The answer is yes, and there has been work from these guys who are responsible for early work in this area, which suggests a number of tests, and one possibility is this one. In certain circumstances and under certain assumptions, A and B interact mechanistically if this inequality, which involves the coefficients of the model, is verified. The problem here is under certain assumptions. First, note that this test is different from the usual standard statistical interaction test, but the problem is not in the test, which is really easy, but in the assumptions. And the work we have done is to first extend this to work with this method, to work with continuous exposures, and second, to reformulate the problem in such a way that it becomes applicable in problems with a complicated causal structure. For example, this slide, which you see now, is, again, you see this FTO story, the gene FTO, which here is represented in terms of a binary variable indicating rare homozygosity of a particular SNP locus within the gene, who influences infarction. It does it in two ways: indirectly via an increase in body mass, and directly, which is basically this arrow. U is the collection of all variables which collude with these variables here in causing infarction, and then we have a certain confounding structure. This regime here is not doesn't have a political connotation. It has to do with an indicator of how the values of A and B are generated, whether interventionally or observationally. And we owe to Phil David a theory which he developed, which shows that the conditional independencies you can draw from this graph, despite the fact that it has this node which actually is not a random variable, make sense, and in which way they make sense. And this morning also Panayota Costantino had a poster which explained in which sense we can draw conditional independencies. And our method is based on this, on the shoulders of this theory, because our methods consist in drawing this diagram and extracting conditional independencies, and the framework we developed allows, on the basis of the conditional independencies represented in the graph and of additional information, to tell us whether it's possible to test mechanistic interaction. If yes, on what variables you should condition, and so on. And we also got into a related territory, which is develop conditions for estimating this direct effect using G computation. So in summary, we are developing methods which use algorithms and causal inference in the hope that this will help the genetic epidemiologists to sort out, make sense of the data. And in fact, our experience is positive. We are applying this in a number of disease areas. For example, here we use the method to explore the role of dysfunctions of ion channels in multiple sclerosis. The idea here is that mechanistic interactions between genes mirror the way that certain proteins interact collaborate in producing the disease. Actually, the way they interact in producing the dysfunction which causes the disease. And this may lead to a good understanding of the mechanism and also to find variants which play a key role in the mechanism, but they are not represented in genetic association studies. We also apply this in Crohn's disease in the study of autophagy. Again, the idea is that epistatic patterns between the genes mirror the way the proteins collaborate in the pathogenetic mechanism. And also another idea is that these epistatic patterns allow to better discriminate different forms of inflammatory bowel disease than genetic association. And also we have applied this to see whether there is whether the response to statins in certain patients at risk of cardiovascular disease depends on genetic variation in a particular region of chromosome 9. Thank you very much.
Nobody has questions? Yeah?
Yes.
Okay, Carlo, if I remember very well from classical ANOVA, the interaction you have to test before you believe it's significant. You have to test if it's not multiplicative. Do you have in your approach the same problem, or is it?
Basically, we have a way of testing for mechanistic interaction, which is actually a test of presence of excess risk or superadditivity in the risks. And whatever model you use on a logistic scale, on a linear odds, or you will basically estimate that particular quantity. So we are free of, we don't have the problem of dependency on the model, and this one is one aspect of it. Thanks.
Thanks, Carlo.